When we look at lattice energies, not only does it tell us how much energy is given off when the crystal lattice forms, it actually also gives us an indication of how much energy would be necessary to break that crystal lattice. Meaning it would indicate if something has a high or a low melting point or boiling point. All crystalline structures have relatively high melting points, but the more or higher the lattice energy, the higher that melting point would end up being. So when we look at a crystal lattice, it is made up of little groups that make the overall shape. And that first little group that sort of sets the whole pattern for building the rest of the crystal is called a unit cell. So we define a unit cell as the smallest portion of a crystal lattice that shows the three-dimensional pattern of the entire crystal. So we can think of a crystal or crystal lattice as a set of repeating unit cells, and that would be repeated over and over and over again in all three dimensions. Ultimately, that builds together to make the crystal. So a unit cell really is just the simplest arrangement that can set the overall shape or structure of what the crystal lattice will be. So if we do a little comparison between ionic and molecular compounds, remember that because an ionic compound is formed with ions that are attracting each other, that attraction is very, very strong. What that means is that ionic compounds have certain characteristic properties based on that strength of attraction. As I already mentioned when we were talking about lattice energies, crystal lattices need a lot of energy to be broken because a lot of energy was given off in their formation, which results in very high melting points for these crystals. They also tend to be very hard but brittle, meaning they're not malleable like a metal. If you strike one of these, they're going to fracture. They're not going to bend. In their solid state, although they are made up of charged particles, they are not conductors, because in their solid state, all of those ions are fixed in a somewhat rigid formation. Although they're vibrating in place, they're not free to move, so they cannot conduct an electric current. But when you do melt these, if you make them molten, or you dissolve them in water, either one of those would allow those ions to be free from each other enough to be able to conduct an electric current. When we look at molecular compounds, these are compounds that within the molecule have quite strong forces of attraction because of their shared electrons, but between the molecules there is not a lot of attraction. And so that intermolecular force is somewhat weak. Those weak forces of attraction between the molecules, called dispersion forces, are going to give covalent compounds molecular compounds different characteristics than ionic. So because the force of attraction between them is low, they have low melting points. It does not require a lot of energy. In fact, many of them not only are liquid at room temperature, they are often gases at room temperature because of how small the force of attraction is between the molecules. Also, they are not conductors of electricity. They are not made up of charged particles. The whole thing is neutral because they are sharing their electrons instead of transferring their electrons. And as a result, they are not conductors in any case. Doesn't matter if you melt them. It doesn't matter if you dissolve them in water. They are not going to be good conductors of electricity. There is, when we deal with ionic compounds, a group of atoms acting together, sometimes called molecular ions or polyatomic ions. So when certain atoms bond covalently together and share their electrons, they occasionally have both the characteristics of molecular and ionic compounds because they form little groups that we would think of as molecules, but they have an overall charge because they either have had to lose electrons in order to make these little molecules work, or they have had to gain electrons to make these little molecules work. So we call this charge group of covalently bonded atoms a polyatomic ion. And if you look on the back of the periodic table that I've given you, there is a list of many common polyatomic ions, and they are grouped according to the charge. Now remember that this charge is not carried by each individual atom that is a part of this polyatomic, but rather the group as a whole has that charge altogether. If we look at metals, metals have a very different way of grouping together. Metals don't react with each other like nonmetals are able to react with each other. Metals do react with nonmetals, as we saw with ionic. But when metals combine with each other, they actually blend together as opposed to reacting and forming new things. Metallic bonds exist within single elements or within groups of these metals. What happens in a metal is that these vacant orbitals in the atom's outer energy levels, so remember that most of these metals that we're talking about have valence shells in the D block that are relatively empty oftentimes, and as a result they have a lot of empty space. What happens with these overlapping orbitals is it allows the outer electrons of the atoms to roam freely, not just around their own atom, but actually to move away from their own nucleus, their own atom, and be attracted to the nuclei of other atoms in that metal. Because of that, we say these electrons are delocalized. It means they no longer belong to just one atom, but instead move freely in this network of empty atomic orbitals. What this forms is known as a sea of electrons. So the metal atoms, the nuclei, the positive parts, and the inner shells of the electrons are arranged very tightly. We know metals to be quite dense. They're packed quite tightly into neatly organized crystal lattices. But surrounding those positive atoms is a whole bunch of freely moving electrons called a sea of electrons. So it might look something like this when the valence electrons that are next to their inner electron shells and nuclei are able to move free from each other. The positive part, the cation of the metal, stays organized into its nice, neat structure, and as I mentioned, is very organized and densely packed together. But then all of these outer electrons are free to move within these vacant orbitals. And so these electrons don't stay attached to their own atom, but they are free to move with towards others. That's essentially what metallic bonding is. That metallic bonding gives metals unique characteristics. Because they have free moving electrons, if you try to conduct a current through them, those electrons will be able to move towards the anode or the cathode and will conduct electricity. These free moving electrons also carry energy very well, so they're good thermal conductors. Because of this freedom to move, metals also are very malleable and ductile. And these electrons are free to reflect light very easily as well, and that's what gives many metals their shiny appearance.